Hello everybody. My name is Sam Abrahams, and I'm a Los Angeles-based machine learning engineer. One of the things that I am known for, I don't like saying that, but one of the projects that I'm a part of is the TensorFlow white paper notes. Essentially, it's just this annotated guide to the white paper written for TensorFlow and released back in November. If you guys haven't read it and are interested in how TensorFlow is set up, what its infrastructure looks like, I highly recommend it. It's a very enjoyable, easy to read, but interesting white paper. I also am the maintainer for the TensorFlow for Raspberry Pi. So if you guys are interested in trying out TensorFlow on your Raspberry Pi, trying out some of the distributed functions of TensorFlow, I have binaries up there for both Python 2 and Python 3. So check those out, obviously completely free. And I am a contributor to the TensorFlow project. It's obviously a lot of fun getting the opportunity to work with, even though it's digitally, with a lot of these really talented engineers. And if you guys want to improve yourselves, improve your engineering ability, I highly, highly recommend getting out there, just finding something, right? Anything that you think could be moderately improved, just go out there, give it your best shot, and the people in charge of the TensorFlow project will guide you and help you solve the problem. They won't just do it for you. Okay, so this talk is going to be a sprint. There's a lot of things I'm trying to cover, and I actually want to ask you guys. So it seems like pretty much everyone here is for TensorFlow, which is fantastic. So just by show of hands, timid or not, how many people have used TensorFlow before? Okay. How many people have read about, sort of understand what TensorFlow is? They have a good idea, they've done some research, and they pretty much know what's going on with TensorFlow. Okay. And then how many people have heard about TensorFlow but really don't know very much about it other than it's used for machine learning, it's cool, it's fast, Google made it, and I want to get a part of it? Okay. Okay, so we got like a fairly diverse mix of people. So we'll be going through this, and I'll do my best to be thorough, but at the same time, I don't want to bore those who are using TensorFlow. So we're going to go over some of the core TensorFlow API and terminology. I don't want anybody to be left behind as we move forward. On the whole, TensorFlow isn't a very complex workflow, but I don't want people to get lost when we start talking about graphs and edges and adding nodes and all that. Like I said, we'll talk about the TensorFlow workflow. I want to show you guys some example TensorFlow code, and we're going to try to do a little bit of a mini live coding session. You don't want to have those go too long, but I do want to showcase some really cool features of TensorFlow. We'll go over TensorBoard. TensorBoard being one of the really, really cool visualization software that comes with TensorFlow. It's just like part of the package. It's great. Okay, so let's talk about the TensorFlow programming model. If any of you guys have used Theano before, it's very, very similar. It's another graph-based engine, computation graph-based engine. The user-facing API, so pretty much everybody using TensorFlow on a day-to-day basis is going to be interfacing it with Python. But it is the majority of the actual execution code is written in C++. So that the idea is that we have this very user-friendly, nice Python interface in the front, but the actual meat going on underneath is this already compiled C++ code, which allows it to be much more efficient than something like Python. So the computational code, as I said, is written in C++, and there are separate implementations for either CPU or GPU for each of the functions written in TensorFlow. So if something, in general, everything is capable of being run on CPU, and if they can get additional benefit of being run on a GPU, or if it just is possible to run it on a GPU, even if it isn't highly parallelized, TensorFlow is able to decide to put operations either on the CPU or GPU based on what is possible to go where. if any of you, this is a data science hub, it would seem. So I assume that a lot of you guys are familiar, at least, with NumPy. It's one of the lingua francas of data science. It's the ultimate Python n-dimensional array library. TensorFlow is designed to be completely and utterly integrated with NumPy. You can pass in NumPy objects as if they were TensorFlow objects, and objects returned at the end of TensorFlow runs are actually NumPy objects, which means you can seamlessly go from manipulating your data, passing it into a TensorFlow graph, and then receiving some transformed data, and then playing around with it some more with NumPy. Okay, so TensorFlow programming pretty much at the end of the day boils down to 2 steps. The first step is to build the graph that you want to run. So you build a node, you have all these different steps, right? And you haven't run it yet. Then you use a TensorFlow session to run it as many times as you want. So for machine learning, right, the idea here is that you build a graph, you build your model that will be your prediction step, right? And then you have we analyze the error, then we do some sort of gradient descent. If for a neural network, you backpropagate, right? And then you run it multiple times, with each run corresponding to a single training batch, right? Make sense? Pretty good? Okay, cool. All right, so let's talk about graphs. So at the core of everything is the graph, right? It's the primary structure of TensorFlow. And in general, when you're making your own models, you're only going to have a single graph that you're dealing with. But you should know that TensorFlow is capable of handling multiple graphs. And that may or may not come up later. I don't remember exactly what's going on, but with this guy. But you should know that it's possible to run multiple graphs, and there's no reason not to. In fact, you can think of one big graph, right? You can think of it as being able to be split in half and being 2 separate graphs, if you'd like, right? Nodes represent computations or data transformations. So I don't know how many of you guys are familiar with with basic graphs and graph theory. It's pretty much just circles and lines. But nodes represent computations or data transformations, and edges represent data transfer. So you'll have circles that represent computations like add or multiply or matrix multiply, and then the edges between them, the lines connecting those, are arrows saying, okay, the output from this addition is going to move on to the next node, which might be multiplication. Okay, so we're going to basically go through this. Hopefully this isn't too dull, but I don't want to leave anybody behind if people haven't seen graphs in mathematical form before. So what is a data flow graph? It's also known as a computational graph, right? It's just a very nice way to visualize and abstract mathematical computations. So this is a very simple graph showcasing the addition, right? So we have some input A, we have some input B, right? They move their data. So here we have the number B moving up to this node. We have the number A moving to this node. We end up with A plus B, and then this operation will output the value of A plus B. Pretty simple, right? And the idea is that we can chain these together. We already went through the nodes and edges before, right? So we have nodes representing operations. We have edges representing numbers. So why use graphs? One, they're super highly compositional. That means that they are incredibly flexible for research purposes. So Theano, Torch, a lot of these other machine learning libraries are useful because it allows researchers to kind of put together these very fluid and flexible models without having to worry about whether or not their library can support it, right? If you're using this very heavy-handed layer-by-layer approach, you may not be able to get the sort of flexibility that you're looking for and may not be able to tweak your model to the degree necessary to get that extra percentage of correct estimation. In addition, graphs are useful for calculating derivatives. If any of you guys remember your chain rule, anyone up for calculus? No? If you guys are getting into machine learning, I highly recommend you falling in love with calculus again. Not the hard parts of calculus, just like the easy derivative bits. That's not true. You should learn all of it. Basically, what you can do with the chain rule, if you recall your chain rule, I don't want to like pull out the whiteboard, but basically the idea is that we have a function f of x, right, and we have a function g of x or g of y, right, and then we have the problem of g of f of x, right? And so the goal is to get the derivative of g with respect to x, but we have this y in the middle. We need to figure out how do we get there? And the answer is you take the derivative of g with respect to y and multiply that of f with respect to x, and math happens, and you have what you want, right? So the key with that is that you can, the whole reason they call it the chain rule is that it doesn't just go 2 layers deep, right? It goes very deep. And that's why they call it deep learning, right? So you can basically start with, you can have this layer, a network that is many, many layers deep, goes very far back, and you can get the correct derivative with respect to any of your inputs, right? And if any of you guys have gone through like your basic neural network training, you know that backpropagation is all about calculating the chain rule backwards throughout a graph. Cool? That's another reason why we use graphs. It's also easier to implement distributed computing. This is pretty straightforward. Basically, if you can segment your computation into individual chunks, it's way easier to place them on different graphs and on different threads. And it's already segmented nicely, see? And like I said, neural networks are pretty much already computation graphs. OK, I'll try to sprint through this faster. Tensors, just in case you guys are uncomfortable with that terminology, all they are is an abstraction of a matrix, right? So if a 2-dimensional tensor is a matrix, a 1-dimensional tensor is a vector, a 0-dimensional tensor is just a scalar or just a single number. And then as you go higher, you can have you can imagine a 3-dimensional matrix as a cube if you want, and a 4-dimensional matrix as a hypercube or whatever. In reality, you just think of them as any sort of higher dimensional arrays or matrices, right? If you, in general, in TensorFlow, most of the math actually happens in 2 dimensions anyway. That's not the case for every operation, but in general, if it is easier for you to just think of them as matrices, feel free to do so. I won't judge you, and that's what's important. OK, so just to go over how you would define tensors in TensorFlow for those who haven't seen it, you can either do them as standard Python lists. So you can see up here on the top, we have a scalar. It's just a single number. You can pass this into TensorFlow operations. It'll just read it as a tensor, right? Same thing with a single vector, right? Or we can have a list of lists and have a matrix. Or we can have a list of lists of lists and have a 3-dimensional tensor, and you can go even further. Like I said, you can that TensorFlow integrates seamlessly with NumPy. And you can basically do the same thing. We use the same sort of verbiage, I guess, right? But wrap it in an np.array wrapper. And the reason you would want to do this, and this is actually pretty important. You probably won't see this very much in the slides, but I encourage you as you're learning TensorFlow to use NumPy for this, is you can specify the exact type of data type that you'd like. Python is a very loosely typed language, weakly typed even. And the thing is, TensorFlow has a very robust selection of types available to it, which go all the way down to the C++ implementation. But because Python doesn't have a way of directly specifying whether or not you want a 32-bit floating point or a 64-bit floating point number or 64-bit integer, et cetera, you aren't able to specify that information without using NumPy. So if you use NumPy, you can do exactly that, and you won't have to deal with weird like type mismatch errors as you move along. Okay, so that's piece of advice number 1. So like I said, please use NumPy arrays. I'm not doing it because I'm lazy this time, and its space is limited. Okay, like I said, I've been using the phrase operations. You'll also see the word op. I've been intentionally trying to not say op because of DevOps and that whole field. It maybe can just don't bother with that. I'll say operations with a capital O. They represent any sort of computations, and in TensorFlow, an operation is you'll see it as a Python function. You call it, you pass in your inputs, 0 or more tensors as an input, and it will do any sort of computation. So these computations can be as simple as adding 2 tensors together. They can do something that has nothing to do with math itself, but may initialize variables. They may do other operations that affect the graph in one way or another, right? But the main idea is that you pass in 0 or more tensors, they return 0 or more tensors, and the big thing that may catch some people off is that they don't immediately execute, right? The idea is that what you get after you run that Python function is a handle to that operation, right? You get a handle to the output of that operation. You can pass that output to another operation, or you can run that output and have the graph run to that point. So just remember, when you are dealing with operations, they won't run instantaneously. So when you say, okay, A equals 1, and B equals 2, and C equals TF dot add A plus the A and B, right? You won't get the number 3. You'll get a handle, you'll get a TensorFlow operation, which will, if you run, right, which we'll go over later, will return 3. Okay, hopefully I'm not making it more. Say that again?
Basically, the transformation and the inputs are binded, but not yet executed.
Exactly. So that's exactly it. The idea is that you have access to the operation itself, like the concept of the operation, and it knows that it's taking in those inputs, but it hasn't actually, it's evaluating that lazily, right? So here's just a quick example, right? So we're using the simple multiplication. This isn't matrix multiplication. It's just simple basic multiplication. First, we import TensorFlow. Well, by convention, we shorten that to TF because writing TensorFlow every time is sadistic. We are going to just create, we're going to say A equals TF.mol. And you'll notice we're just passing these in directly. Like, as I said, I'm not using NumPy because I'm a bad person. And what A is a handle to this multiplication node, right? But when we get it, it doesn't return the number 15 yet. What we have to do is start a session, and we'll talk more about sessions soon. And then once we have opened up a session, we can run it, and then finally it returns 15. Hooray! Okay, so let's talk a little bit about placeholders. So placeholders are your input nodes. So you can imagine, as you're running graphs, that you're not always going to want to use static, like you're not going to want to use the same numbers every time you run the graph. When you're doing machine learning, you're going to need to be passing it training data, and you're going to need to be giving it the labels for that data as well, right? So the idea is that you give, for TensorFlow, in order for it to be able to compute matrix multiplications, it needs to know the dimensions of the matrices, right? So when you specify a placeholder, you say, well, TensorFlow, I don't have any data for you yet, but I do know it's going to be 100 by 400, so you can calculate all the other shapes you need to do in order to make sure everything matches nicely. So when you create a placeholder, that's exactly what you do. You give it the data type, and you give it the shape. You can also give, just as a side note, you can give all these nodes names, which I'll be doing in the live coding demo, as it's good practice. But just for the essential things you have to do, you have you just need to give it the data type and the shape. And then you can use my placeholder as you would any other tensor. You can pass that into an addition operation or a multiplication operation or a matrix multiplication operation. OK, now let's talk about actually running a session. OK, so the session is in charge of coordinating your graph. So TensorFlow, by default, has one graph, and it's just kind of hanging out in the background. And as you are coding and adding in more and more nodes, it's keeping track of what's going where, who's outputting to what dependencies are involved, right? And the session is the master of that. And the most important method, as we saw before, is the run method. It's what actually will run the graph and get you what you want. So it takes in two parameters. There's fetches and there's feed dict. So fetches is a list of objects, and those objects are tensors, nodes in your graph, that you'd like to get the results for. And your common example is the final layer in a neural network, but you can actually pass it in any tensor that's in your graph. So the idea is if there's an operation that you would like to run, then you just pass it into the TensorFlow session. And the reason that this is nice is that you can, if you'd like, you don't have to run your entire graph if that's not what you're interested in. And because of the nature of your graphs, it's only going to run the nodes previous, right? The dependencies of that node, and it won't run the entire graph for no reason. Say that again? So by default, it's going, if you just run session.run, it's going to just print it to the console. You can save it as an output, right? So these operations will output 0 or more tensors, right? So for example, if we ran going back to the add, right, or the multiplication, by default, it's just going to print out the number 15. If you can save that to a variable if you'd like, and you can. Are you asking caching as you run?
Yes, I meant
Sorry.
in terms of, let's say, if it's already partially processed a graph, will it not need to reprocess that so that you can incrementally parse?
Yeah. So from what I understand, it will do its best. Though the issue is that for many of the most commonly used graphs, you won't, like when you're doing training, right? It's the caching of data isn't very useful because you end up having a dependency on a placeholder or your input, which changes each time you run, right? But TensorFlow does its best to not waste people's time in memory, right? Going back. OK, and then this feed dict parameter. So we talked about how we have placeholders. There's actually a number of ways to give values to those placeholders, to those input values. The sort of most common way you would see it done these days is when you're not especially when you're not doing a distributed session, is to use this feed dict parameter. Basically, what all the feed dict is you give it a dictionary. That's what the dict part is, where the key that you pass into it is the handle to the node that you want to give the input value to, right? You give it the handle to your placeholder node, and then the value that you in the dictionary is the tensor value that you want to give it, right? So in the previous one, I don't know if I have an example. I can show it in later. Yeah, I can type this in later. But for the previous example, for this placeholder, we would give it a feed dictionary where the key is my placeholder, just no quotes around it, just my placeholder. And then the value would be this 100 by 400 tensor that we want to run. Cool. OK, here we go. TensorFlow variables, these are variables that persist over time and that you want will basically be able to take on different values and slowly change over time or drastically change over time. So maybe like weights in your neural network that you want to train, or any parameters in your machine learning network. Like I said, weights and biases. like you said, if you know machine learning, the final values that you have after you train, these will be the main parameters that you've been trying to get. Before you run in the graph, you have to initialize them, and that's just part of the housekeeping of a TensorFlow session. The basic idea is the TensorFlow has to know when you want, we give the variable a starting value, but it doesn't know exactly when you want to give it that. Because it's possible that you train for a while, and then it's possible that you start at 0, and then you train, and then you're like, I messed up, I want to start again. So there's a node, or there's an operation called initialize variable that you can use to initialize a single variable, and then you can use a helper method for that says initialize all of my variables that will set your variables to the starting value that you give them. Sorry for spewing that at you. So there used to be and still in most of the documentation, you'll see this TensorFlow.variable direct call as the way to initialize your variables. This is okay. But for a multitude of reasons, mainly having to do with trying to give your variables, or pass your variables around to different variable scopes, it's best practice to use tf.getVariable. This is hard to cover without being able to describe what variable scopes are, but the basic idea is you can have variables with similar names that are in, you can have a graph, right? So imagine this big old graph, and we define a variable over in this section, right? And this section, for the most part, doesn't see this section of the graph over here. The big thing, though, is that they have one variable that they both want to be able to manipulate. And it just becomes a lot simpler if you use tf.getVariable because you give it a specific name and you're able to call it from there. So that's the basic idea of why you want to use getVariable. That said, I'm probably going to just end up using TensorFlow.variable anyway because these graphs we're making are pretty straightforward. When you want to update its value directly, you can use the assign method. Okay, so finally we're sort of closing the loop of this intro section. So what we're trying to do here is create this node here, or this graph, with TensorFlow code. So once you create this placeholder variable, you're going to end up with x, right? So we're calling our placeholder x. So bam, we're going to get this graph here. Then we're going to have a TensorFlow variable that's going to have the starting value of 0. And so then that just gets placed onto the graph. Nothing's executed yet, right? And then we're going to create a new node called y, and we're going to have that be the assign method. Or rather, I should say, we're going to assign the value of, we have a node that's going to be the assign operation. And it is going to take in the values of start, which is itself, right? And then also it's going to take in x here. Sorry. So the basic idea is that each one of these lines of code represents an operation, and then the ways that we pass in the values to each other define the edges. Yes, sir.
Sorry for the naive question, but I see just the 3 statements there. So what decides a graph is formed with x and start pointing to the other node?
Say that again?
How does the system determine the node x and node start should actually point to? They're just 3 statements, right?
Yeah. So how does it know that they should move together here? Okay. So the basic idea is, so we start with node x, right? And when we first define the code, we would have just x by itself with no arrows pointing anywhere. It's just a node hanging out in space. We have, as the programmer, have access to its output, right? But for now, all the program cares about is like, okay, x is hanging out. That's all we care about. And then the same thing with start in isolation of x. X is still here with no arrows, but for all intents and purposes, start is hanging out by itself. But once we call this assign method, once we call this assign operation, all of a sudden we start with saying, okay, we're going to place this assign operation. We're going to call it y. But we're just going to have this assign operation placed on the node. So what inputs do we need? Like, what values do we need in order to make this run? And we see, oh, we have a handle for the start, this value start. And then we say, okay, so that means we need to place this operation here because we're taking it in as an input. Technically, this is going to get turned into an add operation, and then the add operation is going to get placed up here. But for simplicity's sake, we're just going to stick with this. So we're saying, okay, we're taking in the start value as an input, right? And that goes up here.
So basically, it's because of the input. So if you said y equals x plus 1, start won't be pointing.
Exactly. So basically, the way it works is it knows that it needs to place an operation down on the graph, and then it looks at its inputs and says, oh, these are the things that I'm dependent on. That means I'm going to have an edge here, right? And so this node, actually, if you look at it, will keep track of its own dependencies, and that's how it knows, oh, in order for me to run, I know that I need both of these guys to have run. I need to know what their outputs are, right? Cool. Any more questions on that? Yes, sir.
Why is it start.assign?
Okay, so this start variable is actually a variable. So this is a TensorFlow variable object, right? So it's not a Python variable. It is a variable object which has its own sets of methods. And one of those methods is the assign method, which is its own, even though it's an internal method, it's still an operation, if that makes sense, right? Yeah, so that's what it is. Assign is a method of...
Very well have been x.assign.
Exactly, correct. Well, I missed the detail.
Could you say, instead of start.assign, could you say x.assign?
Oh, so the thing, x is a placeholder, right? So start is a variable object, right? You can use it as a tensor. It will be converted into a proper tensor object. I'm not sure I don't think it inherits from tensor, but the variable has its own set of methods. A placeholder would have its own, and it doesn't have assign as its own, right? Cool.
Does assign update the value of start?
Yes. So assign doesn't increment it or do something else. It gives you give it the exact value that you want, right? So if you wanted to increment it by 1, you would say start plus 1, if that makes sense, right? What this operation does is it increments start, right? So start, we want to give a new value to start. We want that new value to be start plus some value. Cool?
I guess what I'm just about is why you're having the start variable assigned, and then you have y variable, which is equal to start. Anyway, shouldn't it be like y equals tf dot sum start plus x? That's, I guess.
Yes. I mean, this was, to be honest, I wrote this slide possibly a month or two ago, and I haven't looked at it, and it needed to be upgraded. So yes, it is very poorly constructed. It is still technically correct, but yes, I apologize for the confusion of of that. Right. My goal was to showcase the variable functionality, and it just happened to be done in maybe not the most helpful way.
Yeah, so as we build up these graphs, multiple nodes and chain up, can you have a feedback loop where such that the graph,
right,
the edge feeds back like the control system feedback?
Right. So the question is it possible to have essentially a cyclic graph? Is it possible for at some point where we have all these, again, we have more nodes, and then eventually we have a value over here that says like, oh, what if start equals that, right? And then we end up having this endless feedback loop. So it's a very good question. And the answer in short is no. You can't really, because of the way dependencies work, right? In theory, you end up with a paradox like chicken. What came first, the chicken or the egg? What came first, the start or the operation that came before start, which is also after start. So you'll see graphs of recurrent neural networks that look like we need to have a cyclic graph, right? You'll see. Wish I had a way to draw this out and not scribble on this, but essentially a common. Can I draw on this wall? It looks like it's drawable. Okay. So you'll see recurrent neural network basic things, right? That essentially look like something like this, right? Where they have this, they like feed. It looks like they feed back into themselves, right? And the thing is, this model, this infinite model of recurrent neural networks, is really more theoretical than something that we can actually do, right? We can't go infinitely into the past, and we can't go infinitely into the future. So what we end up doing is what's called unrolling the model, right? So when you see something like this, right, what's actually happening isn't this thing that's feeding back into itself infinitely. What you're actually seeing is something that's closer to. So now, like, we're going to rotate this because there's not a lot of horizontal. So now we're going to say, instead of, it would be like feeding like this. So we're going to say, like, we're checking out this value here, and then we have the same model up here, and we have an output there, and we have this, and it just keeps going up as many times as we'd like. And it may seem difficult to see like how this matches the recurrent model. But the idea is, OK, we started at this point in time here. We feed it into our model. It does some processing. And we're going to observe it out. We're going to observe its output at that time. And then we're going to feed it back into the same model, right? And the key that makes this work is that the weights, right, all the big weight matrices in here are identical, and they are updated at the same time. Okay, and as soon as you do that, you end up with a model that, in effect, emulates a true recursion, right? A true cyclic graph without having the headaches of a cyclic graph dependency. So if you wanted to try to do that in TensorFlow, the reality is what happens is if you tried to reassign start to a value that's, if you tried to reassign the value of start to like a new operation, right? So let's say we now take this, right? Afterwards we say start equals y plus 2 or whatever it is in TensorFlow speak, right? And you're like, oh, did we do it? Did we break TensorFlow? Well, under the hood, what's actually happening is the graph is getting defined node by node. And what's actually happening is this original start that we used is staying right there, right? What would happen is that we create a new node, right, somewhere maybe up here, right? And it says, OK, it's y equals x plus start plus 2, right? So we're like y plus 2. And we're going to call it start. So just because it has the same variable name doesn't mean that it's going to bump the old start off the graph. What we will lose is the handle, because we're changing this Python variable, right? We're changing what that's pointing to. And instead of this, the word start pointing to this, it's going to point to the new operation in the graph. Does that answer your question? Do you feel good, or do you want? OK, sorry. Yes, exactly. I mean, you'll have to ask this guy, but I'm not sure whether, like, are all tensors immutable always? OK, cool. I thought so, but I didn't want to say that because I'm like,
Yeah, indeed, one very confusing thing is when people try to modify one field of the tensor,
yeah.
TensorFlow barks, and
Yeah.
a lot of Stack Overflow questions say, why I can't do this? Say, no, you have to create a new tensor with a different element for that field.
Yeah, cool. But it's a very, very good question. That's like something that's fun to explore. So yeah, that's building a graph and also recurrent neural networks and also unrolling them. OK, so we've already gone through this. I don't want to to basically run this into the dirt. The basic idea is you start a session, you have to initialize the variables, right? So that's what I was talking about before. This initialize all variables is an op, and I forgot to put in parentheses here. You have to run that operation, and then you're allowed to use the variable. Okay, and then this is a terminology thing, the term devices. So a device is a CPU or GPU. It does not mean a computer or a whole machine. A machine can have multiple devices. I don't know if you guys saw this in the news, but Google announced that they've made their own like tensor processing units for their cloud computing. It's gonna be so cool, except they're so expensive and maybe not practical. But you know, kind of fun. So yeah, just know that multi-device doesn't necessarily mean distributed. If you have a regular computer with a GPU on it, you can run a multi-device setup because you can run it on, have part of it execute on the GPU and part of it execute on the CPU, but it all stays within the same machine. Okay, so we're gonna try to turn this into, I feel like I'm going on for a long time, but I don't know what the time limits we have here. But I want to talk about TensorBoard quickly because it's very cool. And if you've worked with TensorFlow and haven't used it, it's very easy to make just a lot of great use out of it. Basically, TensorBoard allows you to visualize your models. It allows you to visualize statistics from your models. And it can help you make sure that you are doing, basically it can help you make sure that you are that your models match what you've sketched out on paper, right? So I want to do a brief live demo. I don't need to get into the crazy details about the scalars, like doing a bunch of summaries, but I want to just show you guys how easy it is to just visualize your graph instantly, okay? So we're going to close out of this. We're going to open up terminal. Let's start this guy up. Okay, so we're going to create a new TensorFlow Python notebook. We're going to import TensorFlow. I wish there's a way to do this. We're going to import TensorFlow, and we're going to import TensorFlow as TF. Okay, so we run this. It's going to go perfect. Okay, so now let's create our basic graph. Okay, so we're going to say A equals some basic tensor, and like I said, I'm a bad person, I'm not using NumPy. So we have this, and then we're going to have B equals, let's do 1, 2, we're going to make this an actual matrix. 1, 2, 3, comma, 4, 5, 6, comma, 7, 8, 9. Cool. So now we have these two tensors that we're going to be able to use. And now we're going to want to do a matrix multiply. So we'll say C equals TF dot mat mul. Let's see if I get these right on the first time. I'm going to say B and A. I can't remember if that's going to be right. Damn, backwards. No, what did I do? Transpose B. What's that right there? I think, or this guy needs to be, yeah, you're right. I think if we do that, maybe. There we go. Thank you. Okay, sorry. This vectors in vectors bad, matrices good. Okay, so now we have these nodes on our graph. And now we can open up a session. And now, just as a demo, we can say session.run C, and we should get the correct array, right? Hooray. But that's not what we're here for. What we're here for is to open up a writer. Is it summary writer or yeah?
You're gonna have to run it for a bit to see the graph, right?
No, it's actually pretty fast. I feel like this isn't opening itself up right. wanted to double check this. Summary writer, we have to pass it in the, we have to pass it in a log directory. So the first value is just my graph, right? So it's going to output some data here. And then we also need to pass it in the actual, the graph of this session. So session.graph. Did I do this right? No, it's not. What did I do wrong here, Fabricio? I feel like summary writer's not right.
The name is right. I think the model.
Hmm?
The model is not yet .train.
Can you use the question mark to use the documentation?
I mean, I just don't see summary writer thing. Who? Deep apologies. We're going to go to the TensorFlow API real quick. Just as a side note, the TensorFlow API resources are actually not trained. Thank you, sir. No, part of the magic is that you don't need to do like we're not going to be going over the crazy like the summary statistics that are available because that's a little bit more involved. So the same thing, my graph, and then we're passing in the graph that we'd like it to write. Great. Okay, so now it doesn't look like much has happened, but if we go into this notebook, we close this out, and then we look. Well, it's going to be huge, but we're going to start a TensorBoard. If we look up somewhere, we should see. Yeah, it's somewhere in there. Okay, let's do TensorBoard, and then we'll say log_dir equals my graph. Okay, great. So now we see that there's something happening. We have something good on port 6006. So if we go to localhost and 6006, we're going to get brought to TensorBoard. And you'll see there's no scalar data. This is what I meant when we're not showing any summary statistics. But if we go to graph, look at that. So we have our inputs here. Yeah, look cool. I knew I did. I knew I was going to make you guys happy at some point. Yeah, so for all my rambling, I sort of know what I'm doing. So basically, you can see that we just wrote in 3 different, and I apologize for all of this. It's just the low resolution on when presenting. But what TensorFlow is this highly interactive, very, very cool way of visualizing your nodes very quickly, right? And so you can see that you have data coming in. You can click on any of your attributes and take a look-see at some of its information. And as this scales up, you can create namespaces which allow you to basically minimize your graph into bigger and smaller spaces. In fact, I can, well, it's not really worth it. But basically, all you need to do, like, to get yourself started with TensorBoard, just add in a tf.train.SummaryWriter, pass in your graph, and you're going to be able to immediately start visualizing your graph and seeing it. And you won't have to worry about anything else. You don't have to do anything else. It's just like, oh, great! I can sanity check to make sure that I'm not doing anything really dumb.
Work backwards so you can write code from your picture.
So unfortunately, TensorBoard is not a live stream. What it does is it saves data to that my graph file or whatever you wanted to call it. But what you should be using it for is basically saying, oh, that doesn't look like what I expected it to. This isn't connected at all, or this is I'm completely missing something, or I forgot to do this, right? So it's really useful as a sanity checker, and it's also, once you start getting used to it, you can use it to actually test your keep track of your training data over time and visualize that. There's histograms and scatter plots and all sorts of other features that I'm not able to show to you in such a short live coding session, but there are things there. Yes, sir? Oh, sorry. So yeah, basically when you install TensorFlow, it comes with, when you install it, it comes with this TensorBoard command. So all you're typing is TensorBoard, and then we're passing in a log_dir flag to pass in the directory that we want to use. Okay, so if you recall in the code in here, I basically said to save it to my graph, and that's why we were able to pass it in here. Cool.
There's ways to show it, like within, or like the notebook too. There's some crazy, like JavaScript where it generates it.
Yeah, there's third party. Yeah, it's very cool, and TensorBoard is one of those things that everybody knows is really cool, but I don't think people appreciate how simple it is to actually start making use of it.
Can you go back to the notebook?
Yes, sir. Why is it so small? Can I do this? There we go. So I'll let people write down this this code really quickly. Any other questions about TensorBoard? I know that there's a lot of features that I didn't cover, but anything else that we went over quickly here? Very, very cool. All right, sir. Yes? Okay, so that's okay, right? So you'll see that scalar data is, so just to describe what you would be doing, right? So this writer is actually a live object, right? It's something that you can open up and close as you would any other file writer, right? So what the writer does is you open it up, and when you pass in the session graph, it just says, oh, okay, because the graph definition doesn't depend on the data flowing through it necessarily, right? It's when we're just talking about there are connections, there are these types of operations are happening, and they depend on these other nodes, right? As soon as you open up, the writer can say, oh yeah, I can write down that, and that's what we get there. But there's a whole lot more we can do with this writer, and that includes a number of summary operations. So if you go to the TensorFlow API and just look up summary, right, and just search for those, you'll see histogram summaries, you'll see scalar summaries, and all of those you pass those into the writer and basically say writer dot add summary, and put the scalar summary in there. You just say, okay, I want to keep track of this weight over time, like every 100 iterations, right? You'll see in sample code, it'll do a modulo of your training steps. It'll say, okay, every 200 steps, I want to save the value of this weight, and I also want to save the percentage correct or incorrect that we got. I also want to get the standard deviation of these variables and whatever, right? So you can. The thing with this is it's incredibly flexible. It is hands-on. You do have to explicitly tell it what you want, but it gives you the power to be able to say what you want to save exactly when. And so when you first load up TensorBoard, it'll say no scalar data is found, and you're like, oh God, I fucked up, but you didn't. Don't worry.
So Sam, what's confusing to me, right? I think like you're getting at this is like, what am I looking for? What am I trying? I'm trying to minimize error. I'm trying.
Right. So I mean,
if you're looking at just a single weight, that's one thing, but we're looking at the whole.
Right. So the people who are doing data science here know that a lot of what we're looking at is how much better is our model doing over time, over training data iterations, and how does it compare to other models in general, and what statistics can we use to basically get a good sense of whether or not it's doing well. You can have your training error, and then you have your validation error, right, and then your test error. But then you can also just look at things like you can create, if you wanted to, you can create a model that is worth constructing p-values for and whatever, right? So the key here, right, is I've just touched like the very, very tip of TensorBoard and introduced it as a way for you to visualize your code, right, as the graph. Because at the end of the day, TensorFlow is all about building a computation graph. And the more and more you can get used to just thinking of your code as, well, I got circles and I got arrows connecting those circles, and this is how I'm going to do it in code. the more comfortable you are with that concept, the more fluent you're going to become with TensorFlow. And TensorBoard is a great way to immediately give you feedback on how your mental image compares to what TensorFlow is showing you. But again, TensorBoard also allows you to do much more sophisticated data analysis, right? As well as just give you, like, doing something as simple as keeping track of your test error over time and giving you that very, the nice downward sloping error rate over time.
Is it really desirable to have like multiple models running, really training, and then you would compare both in like TensorBoard? Like
So you wouldn't need to do that. So the thing with TensorBoard is you run your graph, and TensorBoard saves your statistics, right? So we can close this, we can come back tomorrow, right? And it's just saved in this My Graph folder, right? As much as it's sad that TensorFlow or TensorBoard doesn't work in real time and show you data flowing through your graph and just like, oh my God, I can see little dots flowing. That'd be really cool. But at the same time, it's also kind of nice. It's stable, and you come back to it, and you'll have the same statistics. You can use it as a data dashboard if you're trying to show it to clients, or if you're working with colleagues and you need to show them that. You can basically use TensorBoard as that data dashboard. Yes, sir?
How would you compare the two models? So let's say you have multiple models training, and if you wanted to see your progress, how would you give them? TensorBoard allows that.
Yeah, so I mean, that just comes down to the type of model you're training. So, and this is something that expands beyond just TensorFlow. This is just model comparison in general. So one example of ways you could do it, right? So obviously you have your how, like, does it learn, right? Does your model, machine learning model learn, and at the end of your training sessions, which model has a lower test rate or higher test score? This one way. But then you can change it and be like, well, there's more to it than that. How quickly, right? How quickly does this model train? And you can graph the learning rate over time, right? You can do things that are akin to seeing what you can basically visualize. What if we didn't train on the data enough, right? You look at your training graph, and it's still sloping down at a pretty good clip, and then we just stopped. Let's say we only did 3,000 training iterations, and what if we had done 10,000, right? We might be able to have a better idea of, oh, it looked like this model was still learning. Maybe we needed to just run it for longer, right? So it's the question of how do you know which model is better or how do you compare them? That's basically TensorFlow or TensorBoard allows you to keep track of statistics that you would like, right? Statistics that you would think are important for comparing models, training rate, the size of the model, the number of, you can keep track of the number, you can calculate the number of parameters going on, whatever, though that would stay the same over time.
So like if the complexity is going down in both models, let's say I have added more layers to one and it runs slower, but maybe trains better. I don't really have a way of comparing that.
Well, at the end of the day, for that, it's not TensorBoard isn't gonna be like, check mark, this one's super better, because we just know. With all of these machine learning tools, right? It's not just a magic black box. It's going to be able to do the critical thinking for you, right? At the end of the day, it's what it's going to try to do is be able to present data to you in a way that is useful and digestible.
So have you seen it useful in a real example?
I mean, basically, I use TensorBoard to keep track of my learning rates. Like I said before, your test validation, training error. Projects I'm working on right now. I am working on a parking meter predictive parking meter application, right? And so we're able to take a look at the percentage of parking meters available at a given time, and we can filter that by location, right? We can decide which which areas we want to track for a given cycle and have that feed into TensorBoard. We can have TensorBoard do we can do it by block and have TensorBoard keep track of all of the blocks at the same time and have it just be this giant grid. That's not that's a little overwhelming, but you can do it like that. But at the end of the day, it's just a nice way to be able to graph information from your graph.
Like the setup, graphing the setup is more important than just looking at how it trains and how sort of the snapshot that.
Well, I mean, again,
Put that here, right?
yeah. So I would say that if you're in terms of like comparing your model, right? You can't look at looking at the graph of the model isn't going to give you a better way of saying, oh, this model is better because just look at it. Just look at how much better it is. Yeah, no, that's better for debugging your code, right? The use of being able to look at your graph is being able to keep track of making sure that when you're doing these models, I find it very useful to actually draw out what my inputs are, what the matrix sizes are, what's being connected to, if I'm inputting some autoencoder off to the side, right? Draw that in and make sure that I have all my inputs transformed correctly. So I would say that yes, sir. I would say that the graphing thing that I just showed you is good for debugging and visualizing your code, and the summary statistics are good for analyzing the success or the actual training of your model. Cool. Yes, sir.
Does the training have to be finished to write it out, or can you track like scalars in real time in the graph?
So what will happen is you'll run your session, right? And what you'll end up doing is having you'll have a writer operation, right? A summary op. You'll write out all the different summaries that you'd like, and then in general, the useful thing that people do is use an operation called, I think it's collect all summaries or merge all summaries. And so merge all summaries, all it does is says, okay, I'm going to find all of the summaries, I'm going to bunch them all together so that we can easily run those. And then, let's see if I can do this all right. So,
The next question is, you just hit refresh every 5 seconds?
So I believe, unfortunately, this is something that I would hope will be updated soon. But TensorBoard will pretty much read the data once when the server's running. And so in order to update with new data, you'll just have to Control-C and then hit TensorBoard again. I may be wrong with that, but in my experience, it's the server doesn't try to reread data as it changes. So that is...
One thing we'll do at the workshop is spend a lot of time on TensorBoard.
Mm-hmm.
That was one thing, is I wanted to see
Yeah.
more on that, but
Yeah, I don't want to hold this guy's got
you have 5
cool
slides
stuff.
that look good, so can we get through them?
I hope so. Is there any more last minute? I know there's TensorBoard is. I didn't really get deep enough into it to be able to satisfy your desires, but are you feeling good?
Like a complex one,
Mm-hmm.
and then yeah, I saw it on your screen, so maybe you could
Yeah.
talk a bit about. Okay.
Cool. So we'll showcase some more intricate examples of that. And so I'll really try to do this as fast as I can. But I just want to go over, if you want to get deeper into TensorFlow, right? It's because pretty much everything I talked about was fairly high level, and for people who just had a either just heard about it or haven't really practiced with it. Okay, so let's talk about. Yeah.
Quarter to 9, the advanced part comes
Yeah, right. Okay, and unfortunately, I don't have a huge amount of time to talk about this. Yeah.
Even the intro? Okay.
Yeah, hopefully you guys are learning something and not feeling like this is too slow for you all. But let's talk about the code base, because TensorFlow is a very cool framework. So As Chris talked about, it starts at the bottom and then it stacks up from there. So at the very root of TensorFlow is your standard C++ library, including heavy use of the eigen library, which if you haven't seen before, check it out. It's very cool, highly optimized implementations of matrix math, right? Then on top of that, we have the TensorFlow core framework. That's where you have your graphs, you have your matrices in C++, you have your operations in C++. And then on top of that, right, so you have the enterprise level structure. Then you actually have the implementation of that, and that's in your the TensorFlow/core/kernel, right? You actually see the detailed code, and you'll have your your CPU implementations, you'll have your GPU implementations. Great. Those get compiled, and then we need to figure out a way to connect those to Python. So we use Swig. Swig is a way of connecting like C++ compiled code and hooking that up into higher level languages. In this case, we're using Python. And then you have all the Python library on top of that, okay? So
Sam, what's the difference between eigen and like a cuBLAS, or what's the relationship between those? Like, why did they choose eigen?
from what I understand, eigen has a lot more focus on scientific mathematical implementations. So you have very efficient implementations of like the hyperbolic tangent function, right? Things that are useful in data science that you may not see from the more rudimentary, though very, very useful arithmetic operations that you'd see in other libraries.
Who maintains eigen?
It's a Tux family suite, so I'm not exactly sure the.
One or two also. It's an external.
Okay.
They don't always. It's so deeply integrated that they always talk about eigen and.
Okay, so Google-ish, but yeah, it's.
Are there other projects that use? I mean, this is the right.
I mean, it's something that I did more research on after I saw TensorFlow. It's got pretty good documentation, though the website does look like it's from 1997. But I highly recommend checking out eigen, because if you're interested in getting into implementing your own code in TensorFlow, if you know C++ or are interested in learning more about this sort of implementation, learning eigen, or at least getting a good sense of the basic eigen APIs, will give you a much more comfortable time looking at the TensorFlow code, as it calls a lot of eigen code. So for the rest of this talk, I'm going to try to go over just the structure of the TensorFlow repository, because it's not explicitly made clear what's what and where you'll find things, right? And then I just want to quickly go over some basic concepts. If you are already doing it or thinking about getting into implementing your own operations, we're going to be doing more of that at the workshop next Saturday. But it's just too much to try to cover, as you guys see how long it takes me to get through the basics. We weren't able to be able to showcase a real operation. But we're going to go over the structure of the code and then talk about basics, and then I'll pass it off to Fabrizio. So,
By the way, all the code from the workshops is going to be totally made public. This isn't, we're not keeping it. It's just we just don't have time for it tonight.
So basically, when you get into your TensorFlow, you go to the TensorFlow repository. It's structured like a Python project, which means that the first folder that you need to go into is actually called TensorFlow, right? So you go to the main repository, you have the README, you'll see a bunch of, you see a folder called third party, and you'll see some other things. Just for the meat of the actual TensorFlow implementation, go into the TensorFlow folder, and then from there we're running. So the big important folder that you'll see is core. So core has all the C++, pretty much all the C++ implementations. It has the kernels, it has the framework itself, and it has the so-called registration of the operations. So inside of TensorFlow/core, you have these further folders. Ops is the registration of the operation signatures. the way that TensorFlow works is that it has a fairly sophisticated and integrated way of basically saying, okay, I'm going to have these operations available to me, and in order for this to run, it needs exactly these parameters, right? So that's registered in core/ops, and then in the kernels is the actual implementation of this code, right? You'll see some files that end with .cuda.cc, is that right? And those are the GPU implementations. And then you'll see files that are .h, your header files. You'll see .cc files. But if you want to just look at pretty much all the operations in TensorFlow, you can go right into core/kernels. If you go into core/framework, you'll actually see the enterprise edition, big, like the structure, right? The bones holding everything up. And then inside a platform are the abstractions that allow them to basically abstract away different operating systems. Then if you go, instead of going into the core folder inside of TensorFlow, you go into Python, you'll see the Python implementations. You'll see wrappers, you'll see testing, you'll see gradient implementations, and you'll see the fundamental Python code. Something that I wanted to write in, if you install TensorFlow, there's files in your installed version that you won't see in the repository, the so-called gen files. And if you want to really see sort of what's going on, you can go into your either Python or Anaconda folder, find your Python library, and look at those gen files. And then finally, there's the contrib folder. There are other folders in there. But the last main one is this contrib folder, and that contains contributed files or parts of the TensorFlow project that aren't fully adopted yet. And then basically there's so much documentation inside the code that the only way that has yet to be written properly in tutorials, that the only way to get yourself into fully to understand it is to dive right in and start reading the documentation in the code. Luckily, the Google does a very good job at documenting their code with comments. So just if you don't understand something, just go in and go in deeper, right? If the easiest way to get in there is if you see a function or a class that you don't understand, go up to the top of your C++ file, look for the include statement that looks like it goes with it, and open up that file and start sort of diving deeper and going down and deeper down the rabbit hole, right? And each one of those should have really solid explanations, and it's just going to be a wild romp. And I had some things so it's like, just so you know, this TensorFlow C++ implementation stuff isn't fully documented. It's not documented anywhere except in code, right? So the only way to know how to use a tensor when building an operation is to actually look in the documentation itself, or look at the code itself. Okay, I think I'll leave it at that. I've been somewhat files worth checking out. I mean, there's just a lot of very cool utility files, very cool classes that are included in the TensorFlow library that aren't mentioned. There is a how-to on the TensorFlow website called adding an op, right? How do you add an op in TensorFlow? But for many purposes, it's not really complete. It goes over the high-level view, right, of what you need to do, but it doesn't talk about the actual C++ API that you need to call in order to make the tensor do the thing you want to do, right? So there are a lot of really useful macros and classes that are available in the library that is being used in the code, but isn't made explicitly clear to contributors. So I encourage you guys to go in there, just start crawling and diving. It's incredibly well documented. So just get in there, learn the code, and have a good time with it. And again, if you want to contribute, they do a fantastic job of really making you feel comfortable with your code and making your code better, right? And it's your code that's getting better. It's not them It's not them changing it and then being like, thanks, I guess. It's just like, okay, here's the thought, try this. And then you work on it and you give it back to them. It's a solid back and forth.
So the term kernel here, I mean, in CUDA, yeah, that term.
Oh, yes. So, yeah. So in CUDA, like GPU processing, you have the idea of a kernel that is the code that's going to run on each of your threads, I believe, right? More or less, right? In TensorFlow, the kernel is simply a C++ implementation of an operation, right? It's the code that's actually running when you call your Python function at the top, right? Cool?
So it's specific to CUDA, or there's...
No.
Because back there, you had kernel.
Yeah, so the thing is the term kernel is used all the time these days. You use it as, kernels are used for image processing. They're used for, it makes sense with convolutional, yeah, exactly. Convolutional neural networks, which often are used for image processing, right? In TensorFlow, when you hear kernel in general, that just means an operation implementation, or yeah, that's what that means.
Each time, so there could be multiple kernels per operation?
Yeah, so basically you can have a kernel for standard CPU implementation, then you can have a kernel for GPU implementation and TPU implementation.
And right, so do people submit their own kernel implementation that's faster than the Google one?
In fact, they do. There's this long-standing, is it the LSTM operation that this very, very talented contributor has been working on, and it's supposedly 50% faster than the current LSTM operation. So yeah, if you know that this isn't done right, you feel free to re-implement it yourself.
Yeah, this sounds very similar to Spark, like when people back in the early days thought that they could get their ML implementations into the code base and they would prove that they're faster, and the Spark people would say, no, put it in Spark dash packages and things like that.
Yeah, the TensorFlow people are, for better or for worse, there's an incredible amount of attention being paid on just raw speed, right? Which is important when you're training very sophisticated models. And because of that, the Google team working on this is very interested in having correct, fast implementations happening. So if you know that there's a better way to do this as a faster implementation, you go for it, right? Because they will love that, right?
Yeah, so what's Google keeping out?
People, I love, I know people saying oh, Google's holding out on the good stuff from us. Google, you tease us. Here's the thing, right? Google is really interested in having as many people learning this software as fully as humanly possible. From what I understand, right, and from what I can tell, and from the actions of the developers over time, the only parts that are not in TensorFlow, right, especially at this point, are the things that are so deeply ingrained within Google's internal infrastructure that it isn't even relevant to TensorFlow by itself, right? So they work their butts off to try to get the distributed implementation out, which is what we're going to look at next. And they're constantly just taking internal changes and pushing them to the public repository, right? They want people to know this. They're interested in having people who know TensorFlow possibly come in to work with Google and not have to worry about having to learn TensorFlow from scratch, right? So Google has no reason to hide the good stuff, really. They would rather have more people use TensorFlow so that they can have more collaboration and have more good implementations come in from the public.
Yeah, see, I get nervous. Right, yes, I saw Guava when they first open source Guava, and they didn't take anyone's contributions, right? It was an open source project that no one could actually contribute to.
Yeah, Google does a very good job of trying to like, even if the initial code isn't up to par, they work very hard to try to make it good enough, and they want the people contributing to feel like they're valued, right? And yeah.
Yes. How long has your like pull request been out there? Did they ever take it?
Yeah, it's a bit. Some of those take a bit.
Is it really like special? Yeah, because you were like adding operations, right? And maybe they didn't feel the operations. I'm just playing devil's
Yeah. So Fabrizio, one of the many things that he's contributed, he implemented the AdaGrad optimization. He did that implementation for TensorFlow. And so it's like that was a pretty lengthy and intensive contribution. Mucho props, muy props.
What's AdaGrad? That's stochastic. So that's like gradient descent, but a different.
It's a form of.
It's yes.
The formula how you compute.
Yeah, the exact number that you use as your vector is different for different reasons, right?
It's an optimization.
Exactly. You can think, for all intents and purposes, you can look at it the same way you would regular gradient descent or stochastic gradient descent or anything like that. In any case, thank you so much for putting up with my incredibly long presentation. Thank you so much for sticking with me.